Section 4, energy and enthalpy for reactive systems. This is where chapter 13 gets really interesting and slightly more challenging. We need to rethink how we assign enthalpy values when substances change identity during a reaction. The problem. Why standard table fail for reaction? Up to now, whenever we need enthalpy values, we use steam tables or ideal gas tables like table A23. These tables work perfectly for systems where the same substance enters and leaves a control volume, like a steam turbine or compressor. But consider this reaction. H2 plus half O2 will form H2O. Hydrogen enters the control volume, as well as the oxygen enters, but neither exits. Liquid water exits, but it didn't enter. We can't take enthalpy differences for the same substance from inlet to exit because the substances are different in and out. The problem is that different tables use different arbitrary datums for their enthalpy values. If I add the enthalpy of H2 from one table to enthalpy of O2 from another, the arbitrary zeros don't cancel. The numbers are meaningless together. The solution is to establish a single common datum for all substances. This is achieved using the enthalpy of formation. We define the standard reference state as temperature T reference is equal to 298.15 Kelvin, which is equivalent to 25 degrees Celsius. And pressure P reference to be 1 atm. At this standard state, we assign an enthalpy of 0 to stable elements in their natural occurring form. C solid graphite is 0, H2 0, N2 0, O2 also 0. For any compound, the enthalpy of formation H naught F is the energy released or absorbed when 1 mole of that compound is formed from its elements, all at the standard reference state. If H naught F is negative, the formation reaction is exothermic, which means energy is released. If H naught F is positive, the formation reaction is endothermic, energy is absorbed. For example, CO2 has H naught F equal to negative 393,520 kilojoule per kilomole. This means forming CO2 from C and O2 releases 393,520 kilojoule per kilomole, which is a very lot amount of energy. You can look up the H naught F values for all common species in table A25 of our textbook.